Okay, this is the second question, homework exercise 6.3. It's an extension of the question that we just completed. So what you're going to be doing here is you're going to use that sample you just built to answer the following questions. So you got B, C. So those right here, 6.3a, 6.3b, 6.3c. And I'm going to have you do what you did in the previous assignment over again so that those statistics are handy and we don't have to hop back and forth between screens. All right, so let's go back and get your random sample. So you go back here and get the one that you generated. So of course, your random numbers are a little different than mine, so you got a different sample than I do. But that's okay. So just copy the data. So long as you follow what I'm doing, you're going to get answers that are pretty close. I think that had the header in it. Yep. Okay. So that's your sample that you brought across. Starts at 52,780, and it ends at, I just want to double check, 5113.4. So they all came across. Yep, beautiful. Okay, so let's do these over again. You did them in the previous assignment. It's good practice. Get the average of this column. So that's the average salary of your sample. Get the standard deviation. So that's STDEV.S. Highlight the salaries again. And a little slow. There we go. And now we got to count the number of yeses that took the training programs. Remember that's equals count if. You get the range of yes and no's. Once you get that, put a comma, quotes, yes, quotes, and close the parentheses. And that'll do it. So we got 30. So now we take, to figure out P, we get count, which is 30 over 50. Whatever you got for count, you have to use. So whatever you got here goes in the numerator. Okay, so 6%. All right, so let's talk about what this new learning is. Obviously, just taking one sample of 50 is probably not the best idea. We probably should take more than one sample. But there's a shortcut. There's some statistics that have been determined, some formulas, I should say, that have been determined that would help you figure out the strength of this particular mean that you've calculated and how close it is to the population of the 2,500 that's there in the data set, right? So that's called standard error. And there's a simple little formula that we can use to help us figure out, based on our sample size, what that standard error is. So in other words, what's the margin of error around this mean that we should be counting on based on the fact that we used a sample of 50 here. So what I'm going to have you do is run this out. I'd like you to do it for a sample size of 30, a sample size of 50, and a sample size of 100, so that you realize that the bigger the sample size that you use, the smaller chance that your statistic here is going to be off. And that makes sense, right? The bigger your sample size, the more valuable this number should be, because it's picking up more data points, right? So it should be more valid. So you just take, it's real simple, you just take the standard deviation you got for this particular sample that you created, and you divide that by the square root of the sample size. So I asked you to do 30 just because I wanted you to see it. 50 would actually be the correct answer for this, because this was based on 50 data points. And then I'll have you do 100 as well, just so you can see what happens. So this one's at 30. Now if we wanted to copy that down, we got to anchor this. So we can copy that down and then change this one to a 50 and change this one to 100. So I just wanted you to see what happens. So the margin of error starts to decline as the sample size that you're using goes up. So that's what this is asking you for. What's the advantage of a larger sample size? And the advantage is a larger sample improves the margin of error or standard error size. Okay, so we have a smaller bracket around the mean. So we say that we estimate that this is a closer approximation to the 2,500 mean, right, the total population mean. And we say the margin of error around that statistic is much smaller. So the bigger your sample, of course, makes common sense. The bigger your sample, the less error you can anticipate in terms of this statistic being representative of the population in which you're working from. And we can do the same thing with a nice little shortcut formula on the P statistic that you calculated here. So we want to know what's the margin of error around this, given that we have a sample size of 50. So that, be careful with this one. You got to make sure your parentheses are good. So it's equals square root, open parentheses. Whatever you have here is what you want to use. So we'll cell reference. So yours might be a little different than mine. Close, but a little different. That, and then times, open parentheses, 1 minus that. So whatever you got there. Close that up. And then divide by, we have n is 50, right? So we're doing 50 total population. Okay. So that's the answer that I got there. Yours is going to be slightly different if your P count was different than mine. Which more than likely it's a little bit different because they're randomly generated samples. Okay, that's the process you would go through to get the answers to this question. I will do the next exercise in a separate video.